We usually imagine telescopes as machines that simply look farther away. You point them towards something distant, gather more light, and see it more clearly. But with the newest generation of space telescopes, something stranger happens. The farther away you look, the further back in time you actually go. And with the James Webb Space Telescope, that journey has reached a moment so early in cosmic history that it begins to feel almost impossible. Webb has observed galaxies that existed when the universe itself was less than 400 million years old. To put that gently shocking idea another way, the light entering Webb's mirrors tonight began its journey before our planet existed, before our sun was born, before the Milky Way had taken anything like its current shape. We are now detecting ancient structures that formed not long after the universe first learned how to make stars, and once you understand how that is possible, something even more surprising begins to emerge. The early universe may have grown complex far sooner than anyone expected. If you enjoy journeys like this, slow, deep explorations of the universe before sleep, consider subscribing. It helps the channel continue making calm, thoughtful stories about reality itself. Now let's begin with something simple. Every time you look at the moon, you are seeing the past. Not by much. Light takes about 1 1/3 seconds to travel from the moon to Earth, so the lunar surface you see is technically 1 second old. If the moon vanished instantly, we would still see it shining there for a moment before the news arrived. That delay may feel tiny, but the principle scales perfectly. Look at the sun and you're seeing it 8 minutes ago. Light from the sun takes 8 minutes to reach Earth. When sunlight warms your skin, those photons began their journey while you were doing something else 8 minutes earlier. Now extend that idea outward. The nearest stars lie several light years away. When you look at them, the light entering your eyes left those stars years ago. Some of the bright stars in our night sky are hundreds of light years distant. Their light began travelling toward Earth before modern telescopes even existed. Astronomy has always been a kind of time travel, but telescopes change how far that time travel reaches. The larger a telescope becomes, the more light it can collect. A bigger mirror acts like a larger bucket catching raindrops during a storm. With enough collecting area and sensitive detectors, a telescope can gather incredibly faint light that has been travelling across space for billions of years. And once you begin collecting light that old, the universe starts revealing earlier chapters of its story. For decades, astronomers have pushed this boundary steadily deeper into cosmic time. Each generation of telescopes reached farther than the last. The Hubble Space Telescope, launched in 1990, gave humanity its first clear view of galaxies when the universe was only a few billion years old. Later observations pushed that limit further back, revealing faint objects from even earlier epochs. Yet there was always a point where Hubble began to struggle. Not because those early galaxies did not exist, but because their light had changed. The universe is expanding. Space itself stretches over time, carrying galaxies away from each other like raisins drifting apart inside rising dough. As this expansion happens, the light travelling through space stretches along with it. Its wavelength grows longer, and when light stretches enough, it moves beyond the colours visible to human eyes. Blue shifts toward green, green toward yellow, yellow toward red. Keep stretching it long enough and it slides entirely into infrared light, a form of radiation our eyes cannot see but which sensitive detectors can measure. This matters enormously when we look toward the earliest galaxies. Those galaxies formed so long ago that their light has spent more than 13 billion years crossing the expanding universe. During that journey, cosmic expansion has stretched those ancient photons far into the infrared. Hubble was built mainly to observe visible and ultraviolet light. It could glimpse some early galaxies, but eventually their light slipped beyond its reach. That is where the James Webb Space Telescope enters the story. Webb was designed from the beginning to see the infrared universe. Its mirrors span about 6.5 meters across, unfolding in space like a golden flower. Those mirrors gather faint infrared photons that have travelled unimaginable distances through the expanding cosmos. The telescope sits nearly 1.5 million kilometers from Earth, in a region called the Sun-Earth L2 point. There, shielded from heat by a vast layered sunshield, Webb can remain cold enough for its infrared instruments to function with extraordinary sensitivity. In that quiet, distant location, Webb waits. and every night it collects light that began its journey billions of years ago. Among those photons are some of the oldest signals humanity has ever detected. To understand how far back this reaches, we need to briefly step outside our everyday sense of time. The universe is about 13.8 billion years old. That number is difficult to feel directly. Human history occupies only the thinnest sliver of it. Written language stretches back perhaps 5,000 years. Agriculture perhaps 12,000. Even the earliest stone tools appear only a few million years ago. Compared to cosmic time, those numbers barely register. So astronomers often compress the age of the universe into a single calendar year to help our intuition. If the Big Bang happened at midnight on January 1st, galaxies begin forming in the first months of that year. Our Milky Way emerges later. The Sun and Earth appear around early September. Complex life rises near December. Human civilization arrives in the final seconds before midnight on December 31st. Within that compressed calendar, the galaxies now observed by Webb formed during the earliest months of that cosmic year. We are seeing structures that existed when the universe was less than 400 million years old. In the calendar analogy, that corresponds to late January, almost the beginning. Yet here is the astonishing part. When astronomers began examining Webb's first deep images, they expected to see extremely primitive galaxies, small, dim clusters of newly forming stars, fragile structures only just beginning to assemble. Instead, some of the galaxies appearing in those early observations looked unexpectedly bright, unexpectedly massive, unexpectedly developed. The universe, it seemed, may have started building galaxies faster than many models predicted. Imagine walking into a forest expecting to see seedlings just emerging from the soil, only to discover small trees already growing there. That was the feeling among many astronomers as the first Webb data arrived. But before we explore why that matters, it helps to step even further back, to a time before any galaxies existed at all. Because the earliest universe was not filled with stars. For a long stretch of cosmic history, the universe was completely dark. And understanding that darkness is the key to understanding why these observations are so extraordinary. Immediately after the Big Bang, the universe was incredibly hot and dense. Matter and radiation filled every region of space. In those earliest moments, atoms themselves could not exist. Temperatures were simply too high. As the universe expanded, it cooled. Roughly 380,000 years after the Big Bang, temperatures dropped enough for electrons and protons to combine into neutral hydrogen atoms. When that happened, light was finally able to travel freely through space without constantly scattering. That ancient radiation still fills the universe today. We detect it as the cosmic microwave background, a faint glow that represents the universe when it was only a few 100,000 years old. After that moment, the universe entered a very different phase. There were atoms now, mostly hydrogen and helium, but there were no stars yet. No galaxies, no sources of light. Space was filled with dark gas drifting under the influence of gravity. Astronomers sometimes call this period the Cosmic Dark Ages. It lasted for hundreds of millions of years. During that long stretch of time, gravity slowly pulled matter into denser regions. Invisible halos of dark matter acted like scaffolding, gathering gas into growing clumps. Inside those clumps, something remarkable eventually happened. The first stars ignited, and with them, the universe lit its first fires. Those earlier stars were probably enormous compared with most stars today, massive, hot, and short-lived. They burned through their nuclear fuel quickly, producing intense ultraviolet radiation that began altering the surrounding universe. Around those stars, the first primitive galaxies began to form. These were the ancestors of everything that would follow. And it is precisely this era, the moment when darkness first gave way to light, that the James Webb Space Telescope is now beginning to observe directly. When Webb detects galaxies from less than 400 million years after the Big Bang, we are seeing the universe shortly after those first cosmic fires began spreading across the darkness. We are witnessing the earlier structures assembling themselves. And the more we look, the more complicated that story appears to be. Now imagine standing on a perfectly dark plain. No cities, no campfires, no distant lights on the horizon, just darkness stretching in every direction. Then, somewhere far away, a single flame appears. A little later, another, then several more. Slowly, across that vast dark landscape, scattered points of light begin to emerge. This is a useful way to picture the early universe after the cosmic dark ages ended. For hundreds of millions of years, space had been filled with cold hydrogen gas drifting inside invisible structures shaped by dark matter. Nothing shone yet. There were no stars to illuminate the darkness, no galaxies to gather them together. Gravity was working quietly the entire time. Dark matter halos, huge clouds of invisible mass, were slowly pulling ordinary gas toward their centres. The process was patient and subtle. Gas cooled, density increased, tiny irregularities in the distribution of matter gradually amplified under gravity's pull. Eventually, in the densest regions, the pressure and temperature became high enough for nuclear fusion to ignite. The first stars were born. Those early stars were likely very different from the ones we see around us today. Modern stars, including our Sun, contain many heavy elements, carbon, oxygen, iron, created by previous generations of stellar explosions. But in the young universe, none of those elements existed yet. There had only been the Big Bang. And the Big Bang produced mostly hydrogen, helium, and a trace of lithium. So the first stars formed out of extremely simple material. Without heavier elements to help cool the gas efficiently, those early stars probably grew much larger than the Sun. Some models suggest they may have reached tens or even hundreds of times the Sun's mass. They would have burned fiercely, brilliant, and brief. Many of them likely lived only a few million years before collapsing or exploding, scattering the first heavy elements into surrounding space. Those elements then enriched the gas that would form later stars and galaxies. In other words, the first stars were cosmic pioneers. They changed the chemistry of the universe itself. But here is the subtle point that matters for our story. Even when those first stars ignited, they did not immediately create large galaxies. At least, that is what many theoretical models suggested. The early universe was still young and chaotic. Dark matter halos were growing through mergers and gravitational collapse, gradually collecting gas and building larger structures over time. Galaxies, according to many expectations, should have started small. Tiny systems, faint clusters of stars, simple beginnings that would slowly merge and grow across billions of years. And for a long time, that picture seemed reasonable. Earlier telescopes had hinted at such early galaxies, but they were extremely faint and difficult to study. Astronomers could only glimpse their outlines. The earliest known galaxies appeared small and dim, consistent with models predicting gradual growth. Then the James Webb Space Telescope opened its eyes. One of the most famous early observations Webb produced was an extremely deep image of a region of sky that, to the naked eye, appears completely empty. If you hold a grain of sand between your fingers and stretch your arm toward the sky, the tiny patch of sky that sand grain covers contains thousands of galaxies. That is the scale we're talking about. In Webb's deep field observations, the telescope stared at such a tiny patch of sky for many hours, collecting the faintest light it could detect. The resulting images are extraordinary. Every point of light scattered across the image represents a galaxy. Some are relatively nearby in cosmic terms, perhaps a few billion light-years away. Others lie much farther. And among them are objects so distant that their light began travelling toward us when the universe was still in its infancy. Astronomers identify these ancient galaxies primarily through a property called redshift. As the universe expands, the light from distant objects stretches toward longer wavelengths. The more the light has been stretched, the higher the redshift. High redshift corresponds to very large distances and very early cosmic times. When astronomers examine Webb's images, they analyze how the light from each galaxy appears across different infrared wavelengths. By studying these patterns, they can estimate how strongly the light has been stretched during its journey through the expanding universe. This allows them to estimate how far away the galaxy is, and therefore how far back in time we're seeing it. In the earliest Webb observations, researchers began identifying galaxies with redshift values suggesting they existed just a few 100 million years after the Big Bang. Less than 400 million years. That alone would have been a remarkable achievement. But the story did not stop there. Some of those galaxies appeared surprisingly bright. Brightness matters because it often reflects the number of stars a galaxy contains. A brighter galaxy generally means more stars are shining together, producing more light. When astronomers first began estimating the properties of these early objects, some appeared far larger and more luminous than expected for such an early epoch. Picture returning to our dark plane again. You expect to see scattered campfires just beginning to flicker in the distance. Instead, some of the lights resemble entire villages already burning brightly. Not enormous cities yet, but far more developed than anticipated. Naturally, astronomers approach these results cautiously. Early observations often produce surprises that later analysis refines or corrects. Some of the initial brightness estimates could shift once more precise measurements were obtained. Some objects might turn out to be slightly closer than first believed. Science moves carefully when interpreting signals this faint and distant. Yet even with those cautions, the pattern remained intriguing. The early universe might have been building galaxies faster than many models had predicted. To understand why this possibility matters, we need to look at the role dark matter plays in shaping cosmic structure. Dark matter is one of the most important ingredients in the story of galaxy formation, even though we cannot see it directly. It does not emit light. It does not absorb light. But it exerts gravity. And on cosmic scales, that gravitational influence is enormous. In the early universe, tiny fluctuations in the density of dark matter formed shortly after the Big Bang. Over time, gravity amplified those fluctuations. Regions with slightly more dark matter began pulling in surrounding material, growing into larger halos. Ordinary matter, gas made of hydrogen and helium, fell into those gravitational wells. Inside them, galaxies formed. You can think of dark matter halos as invisible scaffolding. They provide the underlying structure on which visible galaxies assemble. In computer simulations of cosmic evolution, dark matter halos appear first, gas follows. Stars ignite within the densest regions. Galaxies gradually take shape. Over billions of years, smaller halos merge into larger ones, building the grand structures we see today: massive galaxies, clusters, and enormous cosmic filaments stretching across space. This hierarchical growth process has been a central idea in cosmology for decades, and for the most part, it has matched observations well. But Webb's discoveries are probing a period of cosmic history where this process was only just beginning. Less than 400 million years after the Big Bang. At that time, the universe was barely 3% of its current age. Galaxies should have been in their infancy. Yet some of the objects Webb is seeing look surprisingly mature. Not fully developed like modern galaxies, but perhaps more substantial than expected. Which raises an interesting possibility. Maybe star formation in the early universe was extremely efficient. Gas collapsing inside those early dark matter halos might have ignited stars very quickly, producing luminous galaxies sooner than predicted. Or perhaps our models of early galaxy growth need adjustment. Another possibility involves the nature of the first stars themselves. If early stars were unusually massive, they would produce enormous amounts of light, making young galaxies appear brighter than their mass alone would suggest. That would mean some of the brightness Webb detects could come from relatively small systems filled with extremely luminous stars. Astronomers are actively investigating all of these possibilities, and the story continues to evolve with each new observation. But the key point remains extraordinary. We are now directly observing galaxies from a time when the universe was less than 400 million years old. To appreciate how early that is, imagine compressing the entire history of the universe into a single human lifetime. Suppose the universe lives for 80 years. On that scale, galaxies observed by Webb formed when the universe was barely 2 years old. Our sun would not appear until the equivalent of age 74. Human civilization would emerge in the final seconds before the end. Those ancient galaxies belong to the toddler years of the cosmos, and yet their light has survived an almost unimaginable journey. For more than 13 billion years, those photons have travelled across expanding space. They crossed regions where galaxies were forming, merging, evolving. They passed through growing clusters and vast cosmic voids. Eventually, a tiny fraction of those photons arrived at a golden mirror floating in deep space. And from there, they were focused onto detectors built by human hands. That chain of events is almost absurdly unlikely. Yet it happened. And it means that tonight, somewhere in Webb's memory banks, there are signals from galaxies that existed when the universe itself was still learning how to shine. Which leads to a deeper question. What did those galaxies actually look like? If we could travel back to that era, 300 million years after the Big Bang, and stand near one of these early systems, what would we see glowing in the darkness of the young cosmos? If we could step into that ancient universe, 300 or 400 million years after the beginning, we would not recognize the sky. Not immediately. The familiar constellations would be gone. The Milky Way would not yet exist in its present form. Even the background glow of galaxies that now fills our telescopes would be far sparser. The universe was still assembling its first architecture, but it would not be empty. Somewhere in that darkness, islands of light had already begun to form. Those islands were the first galaxies. They were not the majestic spiral systems we see today, with elegant arms winding around bright cores. They were likely smaller, more irregular, sometimes chaotic collections of stars forming rapidly inside young gravitational structures. Imagine a dense cluster of brilliant blue-white stars packed inside a compact region of space. The stars would burn intensely, much hotter than many stars we see today. Their ultraviolet radiation would flood the surrounding gas, carving glowing bubbles in the hydrogen that filled the early universe. Around those stellar clusters, clouds of gas would swirl and collapse, feeding further bursts of star formation. From a distance, such a galaxy might appear as a bright knot of light surrounded by faint halos of glowing gas. Primitive, but unmistakably alive. These galaxies would have been the first long-lasting sources of starlight the universe ever produced, and their light began transforming everything around them. To understand why that matters, we need to think about what the universe was like before those first galaxies appeared. During the cosmic dark ages, the hydrogen gas filling space was neutral. Its atoms held onto their electrons. That neutral gas absorbed certain wavelengths of light very effectively, especially ultraviolet radiation. But when the first stars ignited, their powerful radiation began stripping electrons away from surrounding hydrogen atoms. This process is called ionization. As more stars formed inside early galaxies, regions of ionized gas expanded outward, like glowing bubbles in a dark ocean of neutral hydrogen. Over time, these bubbles grew and merged. Gradually, the entire universe transitioned from a dark, neutral fog to a transparent cosmic medium through which light could travel more freely. Astronomers call this transformation the epoch of reionization. It marks the moment when the first generations of stars and galaxies fundamentally changed the state of the universe. Webb is observing galaxies that existed right in the middle of this transformation. We are seeing the agents of reionization themselves. That alone would make these observations extraordinary. But there is another layer of difficulty involved in detecting such ancient galaxies. They are unimaginably far away. The light we detect from them today left those galaxies more than 13 billion years ago. During that time, the universe expanded enormously. The galaxies themselves have moved far beyond the distance their light originally travelled. In fact, many of the galaxies Webb observes at extremely high redshift are now tens of billions of light-years away in present-day distance. This can feel confusing at first. How can we see something that is now farther away than the age of the universe would suggest light could travel? The answer lies in the expansion of space itself. While the light was travelling toward us, the universe kept expanding the entire time. Space stretched continuously during the photon's journey, increasing the distance between us and the galaxy that emitted it. It is a little like trying to walk towards someone on an expanding rubber sheet. Even as you move closer step by step, the sheet itself stretches underneath you. Over billions of years, the stretching adds up. As a result, the galaxies we see from the early universe are now vastly farther away than the distance their light initially crossed. This stretching also explains why Webb must observe in infrared wavelengths. Light that began its journey as energetic ultraviolet radiation from hot young stars has been stretched dramatically over billions of years. By the time it reaches us, those photons have shifted far beyond visible red light. They glow in infrared, and that is exactly the kind of light Webb was designed to collect. The telescope's detectors are so sensitive that they can measure incredibly faint infrared signals, photons that have travelled almost the entire history of the universe before reaching our instruments. When those photons arrive, they carry information about the galaxies that emitted them. Their brightness tells us something about how many stars might be present. Their colour distribution reveals how much the light has been stretched. Subtle patterns in their spectra can even reveal chemical fingerprints, hinting at the composition of early stars and gas. From just a few faint smudges of light, astronomers can reconstruct a surprising amount of cosmic history. And sometimes those reconstructions raise unexpected questions. In the earliest Webb observations, several candidate galaxies appeared at redshifts suggesting they existed only 300 to 400 million years after the Big Bang. Some even appeared potentially earlier. That pushed observations deeper into cosmic time than any previous telescope had achieved. Yet what caught researchers' attention was not only their distance, it was their brightness. To understand why that brightness matters, imagine two distant cities on a dark planet. If one city shines much brighter than another, it likely contains far more lights, more buildings, more streets, more activity. The same principle applies to galaxies. A brighter galaxy usually means more stars producing light. In the early universe, forming large numbers of stars quickly is not trivial. Gas must collapse efficiently. Star formation must proceed rapidly. Gravity must gather enough material inside a young dark matter halo to fuel the process. Many models predicted that this build-up would take time. Hundreds of millions of years might not have been enough to produce large, luminous galaxies. Yet Webb's early results suggested that at least some galaxies had already reached substantial brightness by that point. Astronomers began asking careful questions. Were these galaxies truly as massive as they appeared? Could their brightness be explained by extremely hot, massive stars producing intense radiation? Might we be observing unusual bursts of star formation, where a galaxy temporarily shines far brighter than normal? Or could our theoretical models of early galaxy growth be missing something important? These are exactly the kinds of puzzles scientists hope new telescopes will create. Because when observations begin probing a completely new region of cosmic history, surprises are almost inevitable. For now, the evidence continues to be analysed carefully. Some of the earliest candidate galaxies have been followed up with more detailed spectroscopic measurements. These measurements spread the galaxy's light into a spectrum, revealing precise wavelength shifts that confirm their distance more reliably. In several cases, those follow-up observations have confirmed extremely high redshifts, galaxies existing when the universe was indeed only a few 100 million years old. Others may eventually shift slightly closer in cosmic time as measurements improve. This gradual refinement is part of the scientific process. But regardless of the final details, the overall picture is already extraordinary. Humanity has built an instrument capable of observing the first few 100 million years of cosmic history. We are now directly studying the era when the universe's first galaxies were assembling themselves. When you pause and think about that fact, it becomes difficult not to feel a quiet sense of astonishment. Those ancient galaxies formed long before our Sun existed, long before the Milky Way became the sprawling spiral we inhabit today, long before Earth gathered from dust orbiting a newborn star. Yet the light they produced has travelled patiently through expanding space for billions of years. It crossed a universe that continued evolving the entire time, new stars forming, galaxies merging, clusters assembling into enormous structures. Eventually that ancient light encountered a mirror built by a species that did not exist when the photons began their journey. A species that evolved on a small rocky planet orbiting an ordinary star in the outer regions of a typical galaxy. A species that eventually learned how to build telescopes and send them into deep space. That chain of events is almost absurdly delicate. If any link in that chain had failed, if those photons had scattered off dust, if our species had never developed technology, if Webb had never launched, we would still be unaware of those early galaxies. They would continue shining quietly in the distant past, unseen. Instead, we are beginning to glimpse them, and as Webb continues its observations, it is slowly revealing something even more profound about the young universe. The first galaxies were not just small lights scattered randomly across the darkness. They were the earliest pieces of a vast cosmic structure that would eventually span billions of light years. And to understand that structure, we need to zoom out even further, because those ancient galaxies were only the first threads in an enormous web that still shapes the universe today. To understand where those first galaxies fit into the larger story, it helps to zoom out far beyond any single object. When we look at the universe on its larger scales, galaxies are not scattered randomly through space. They form an immense structure sometimes called the cosmic web. Imagine a three-dimensional network stretching across unimaginable distances. Long filaments of galaxies run like glowing strands through space. At their intersections sit enormous clusters containing hundreds or even thousands of galaxies bound together by gravity. Between these filaments lie vast cosmic voids, regions so empty that a traveller could cross tens of millions of light-years without encountering a single galaxy. This pattern is not accidental. It is the large-scale result of tiny fluctuations that existed in the universe shortly after the Big Bang. When the universe was extremely young, matter was distributed almost perfectly evenly, but not quite perfectly. Some regions contained slightly more matter than others, differences so small they were less than 1 part in 100,000. Yet gravity is patient. Over billions of years, those tiny irregularities slowly amplified. Regions with slightly more matter pulled in surrounding material, growing denser. Regions with slightly less matter lost material and became emptier. Gradually, the cosmic web emerged. Dark matter halos formed first inside this growing network. Ordinary matter followed. Gas collapsed. Stars ignited, and galaxies assembled along those invisible gravitational filaments. Today we can map this cosmic structure across enormous distances. Surveys of galaxies reveal that the universe resembles a vast sponge or web, with luminous matter tracing out the underlying skeleton shaped largely by dark matter. But here is the crucial point. The earliest galaxies Webb is observing formed when that structure was only just beginning to appear. 300 million years after the Big Bang, the cosmic web was still in its infancy. The first dark matter halos had condensed. Gas had begun gathering within them. The earliest galaxies were lighting up along those initial strands of structure. In a sense, Webb is observing the universe while the cosmic web itself was still being woven. To picture this moment, imagine watching frost form across a window on a winter morning. At first there are only tiny crystals appearing here and there. Slowly they grow outward, branching, connecting, creating delicate patterns that spread across the glass. The early universe was undergoing something similar, but on scales so vast that even light requires millions of years to cross them. The first galaxies were like those early frost crystals, small luminous nodes forming along invisible patterns shaped by gravity, and the light Webb detects from them allows us to glimpse the moment those patterns began to shine. Yet another layer of strangeness enters the story when we consider how faint these objects truly are. The galaxies Webb detects at these enormous distances are not large on the sky. In fact, many appear as tiny smudges, barely distinguishable from a single pixel in the telescope's detectors. Their light is extraordinarily dim. Imagine a firefly glowing on the surface of the moon. Now imagine observing that firefly from Earth. That faint glimmer is still far brighter than many of the distant galaxies Webb is detecting. And yet the telescope can measure them. The reason lies partly in the size of Webb's mirrors. 6.5 meters of reflective surface gather faint infrared photons that would otherwise be lost. But equally important is time. When Webb observes a deep field, it often stares at the same patch of sky for hours or even days. During that time, the telescope collects more and more photons from those distant galaxies. Each photon adds a tiny piece of information. Gradually, a faint signal begins to emerge from the background noise. It is similar to leaving a camera shutter open during a long nighttime exposure. A dark landscape slowly reveals faint stars and distant lights that would be invisible in a quick snapshot. Except in Webb's case, the exposure is capturing photons that have travelled more than 13 billion years to reach the detector. Each one represents a message from the early universe. This is why Webb's deep images contain so many galaxies. Even a small region of sky contains countless faint sources once the telescope observes long enough. Some of those sources lie relatively nearby in cosmic terms. Others come from far earlier times. Astronomers sift through these images carefully, identifying the faintest, reddest objects whose light has been stretched most dramatically by cosmic expansion. Those are the candidates for extremely distant galaxies. From there, further analysis begins. By comparing how bright these galaxies appear at different infrared wavelengths, astronomers estimate their redshift, the degree to which their light has been stretched during its journey across the expanding universe. This process is delicate. Dust, star formation, and other astrophysical effects can influence how a galaxy's light appears in different filters. Researchers therefore use multiple observations and modelling techniques to refine their estimates. In some cases, additional spectroscopic measurements can confirm the redshift more precisely. But even before that confirmation, the pattern emerging from Webb's observations was clear enough to generate excitement. The early universe seemed populated with more luminous galaxies than expected. This does not necessarily mean our understanding of cosmology is wrong. Far from it. The overall framework describing cosmic expansion, dark matter, and structure formation remains extremely successful at explaining a wide range of observations. But it may mean that certain details, especially about how quickly stars formed in early galaxies, need adjustment. For example, if gas cooled more efficiently inside early dark matter halos than previously thought, star formation could have proceeded more rapidly. Or perhaps the first generations of stars were even more massive than current models suggest. Massive stars burn hotter and brighter, producing enormous amounts of ultraviolet light. A galaxy containing many such stars could appear surprisingly luminous, even if its total mass remained relatively modest. Another possibility involves bursts of star formation triggered by galaxy mergers. In the young universe, dark matter halos frequently collided and merged, bringing large amounts of gas together. Such events could ignite intense episodes of star formation lasting millions of years. During those bursts, a galaxy might shine far more brightly than usual. Astronomers are exploring all of these possibilities, but what matters most for our journey tonight is the broader realization that Webb has opened a new observational window. For the first time, we can directly examine the universe during its earliest period of galaxy formation. Before Webb, much of that era existed mainly inside computer simulations and theoretical models. Researchers could calculate how structure might have formed, but observational evidence was sparse. Now the situation is changing. The telescope is delivering real images from those ancient epochs, and with every new observation, the picture becomes a little clearer. Some galaxies appear compact and intensely bright, others seem slightly more extended, suggesting clusters of star-forming regions spread across young galactic structures. In some cases, astronomers detect hints of chemical elements heavier than hydrogen and helium, evidence that earlier generations of stars had already lived and died, enriching the gas with new material. That detail alone tells us something profound. By the time we see these galaxies, multiple generations of stars may already have formed. The universe was evolving quickly. From the ignition of the first stars to the appearance of recognizable galaxies, cosmic history may have advanced faster than we once imagined. But this rapid evolution also brings another question into focus. If galaxies were forming so early, then the processes shaping them, gravity, gas cooling, star formation, stellar explosions, must have been operating with remarkable efficiency. Which leads us to a deeper layer of the story. Because while stars produce the visible light that Webb detects, the true architects of galaxy formation remain invisible. Dark matter still provides the underlying structure. Those unseen halos governed where the first gas clouds collapsed. They determined where the first stars ignited. They guided the assembly of the earliest galaxies that Webb now observes. And understanding how those invisible structures formed so quickly may hold the key to understanding why the early universe appears brighter, richer, and more active than we once expected. To explore that mystery, we need to look more closely at the strange substance that makes up most of the universe's matter. A substance that has never been seen directly. Yet without it, galaxies, including the ones Webb now observes from the dawn of time, might never have formed at all. Dark matter is one of the quietest characters in the universe. It does not shine. It does not glow. It does not scatter light into telescopes. If you drifted through a cloud of it, you would not see it, smell it, or feel it brushing past your skin. And yet it outweighs all the stars and galaxies we can see. Most of the matter in the universe is dark matter, ordinary matter. The atoms making up stars, our planets, oceans, and people, counts for only a small fraction of the total. This invisible material reveals itself only through gravity. Galaxies rotate too quickly for the amount of visible matter they contain. Clusters of galaxies bend light more strongly than their stars alone could explain. Enormous cosmic structures form in patterns that only make sense if large reservoirs of unseen mass are present. All of those clues point toward the same conclusion. Dark matter dominates the architecture of the universe, and it played an especially important role in the earliest chapters of cosmic history. To see why, imagine the universe shortly after the Big Bang had cooled enough for atoms to exist. Hydrogen and helium gas filled space almost uniformly, but dark matter, which interacts very weakly with radiation, had already begun clumping earlier. Long before stars formed, dark matter had started building the skeleton of cosmic structure. Tiny fluctuations in density grew slowly under gravity. Regions with slightly more dark matter pulled in surrounding material. Over time, those regions evolved into halos, vast, roughly spherical concentrations of dark matter, stretching across thousands or even hundreds of thousands of light years. You can picture them as invisible gravitational wells. Ordinary gas drifted through the young universe until it encountered those wells. When it did, gravity pulled the gas inward. The gas compressed. It heated. Eventually, inside the densest pockets of that collapsing material, the first stars ignited. This sequence, dark matter first, stars later, is crucial. Without dark matter halos gathering gas together, the ordinary matter of the universe would have remained too diffuse to form stars quickly. The first galaxies might have taken far longer to appear. Instead, dark matter acted like scaffolding around a building under construction. The scaffolding itself remains largely invisible once the structure is complete, but it shapes where everything rises. When we observe galaxies today, we are mostly seeing the visible layers of that structure: stars, gas clouds, glowing nebulae. But beneath each galaxy lies a much larger halo of dark matter extending far beyond the luminous region. The same was true for the first galaxies. Inside the young universe, dark matter halos began forming early. Smaller halos appeared first. Over time, they merged with one another, gradually building larger structures. This merging process was extremely common. Two halos would drift together under gravity, eventually colliding and combining into a single, more massive system. Gas trapped inside them would mix and compress, sometimes triggering intense bursts of star formation. Each merger reshaped the growing galaxy. Over millions and billions of years, this process built the enormous galaxies we see today. But when Webb observes galaxies from less than 400 million years after the Big Bang, it is catching that process very close to the beginning. Many of the halos hosting those galaxies would have been relatively small compared to the massive halos surrounding modern galaxies. Yet even small halos can ignite brilliant star formation if conditions are right. Gas falling into a halo does not simply settle quietly. As it collapses, gravitational energy converts into heat. Shock waves ripple through the gas. Turbulence develops. Some regions compress rapidly, forming dense clouds where stars ignite in clusters. If the gas cools efficiently enough, that star formation can proceed rapidly. This is one of the puzzles astronomers are now exploring. Did gas cool more quickly in early halos than previously believed? Cooling is essential because hot gas resists collapse. For stars to form efficiently, gas must lose heat so gravity can compress it further. In the modern universe, heavy elements such as carbon, oxygen, and silicon help gas cool by radiating energy away. But those elements did not exist yet in the earliest galaxies. The first stars formed from almost pure hydrogen and helium. That should have made cooling less efficient. And yet Webb's observations suggest that some galaxies may have built up bright stellar populations surprisingly early. One possible explanation is that the first stars themselves changed the environment quickly. When massive early stars exploded as supernovae, they scattered heavy elements into surrounding gas. Those elements allowed later generations of stars to form more easily. Star formation could accelerate. Another possibility is that dense gas streams flowing along the filaments of the cosmic web fed young galaxies continuously, delivering fresh material that fueled rapid growth. Picture rivers feeding a young city. As long as supplies keep arriving, the city expands quickly. In the early universe, cosmic filaments may have acted as those supply routes, channeling cold gas directly into growing galaxies. Computer simulations of cosmic evolution have begun to show this behavior. Gas can stream along dark matter filaments into the centers of halos, feeding star formation without requiring long delays. If that process was especially efficient in the early universe, it could explain why some galaxies appear brighter than expected so soon after the Big Bang. But the story is still unfolding. Astronomers are continuing to observe these early galaxies with Webb's powerful instruments, gathering more detailed data. Some observations involve spectroscopy, where the light from a galaxy is spread into a rainbow of wavelengths. Hidden within that spectrum are faint fingerprints of atoms and ions. These spectral lines reveal not only the galaxy's redshift, but also clues about its chemical composition, temperature, and star formation activity. For example, certain emission lines from ionized oxygen or hydrogen can indicate how vigorously stars are forming inside a galaxy. Other lines may reveal whether the gas contains heavier elements created by earlier generations of stars. Each new spectrum adds a piece to the puzzle. Gradually, astronomers are building a clearer picture of what these ancient galaxies were actually like. And as they do, something remarkable becomes increasingly clear. The early universe was not a quiet, slowly evolving place. It was energetic, dynamic, full of rapid transformation. Within a few 100 million years after the Big Bang, gravity had already sculpted dark matter into halos. Gas had collapsed into those structures. Stars had ignited. Some had already lived and died, enriching the cosmos with heavier elements. Galaxies were emerging. Not everywhere, not yet in the great numbers we see today, but enough that their collective light began transforming the surrounding universe. Those galaxies were also beginning the long process of shaping the cosmic web itself. Every star that formed released energy. Radiation streamed outward, ionizing nearby hydrogen. Stellar winds and supernova explosions pushed gas outward, stirring the intergalactic medium. Gradually, the early universe became more transparent to light. The fog of neutral hydrogen began lifting, and as that happened, photons from distant galaxies could travel farther without being absorbed. This is another reason Webb can see so deep into cosmic history. The universe eventually cleared enough for light to cross enormous distances. That transparency allowed photons emitted billions of years ago to survive their long journey through space. Some of those photons are arriving now. When Webb detects them, the telescope is not just observing distant objects. It is intercepting ancient messengers. Each photon carries a tiny piece of information about conditions in the early universe. Together, billions of them combine into the faint images we analyze today. And those images reveal a cosmos that was already far more active than its youth might suggest. Which raises an even deeper thought. If galaxies were forming so quickly, if stars were already blazing across the young universe, then the transition from darkness to light may have happened faster than we once imagined. The cosmic dark ages may have ended sooner. The universe may have begun shining earlier, and that realization changes how we think about the first few 100 million years of existence itself. Because those were the years when the universe learned how to make light. And the James Webb Space Telescope is now letting us watch that process unfold almost from the beginning. When astronomers talk about the first few 100 million years of the universe, they often use a phrase that sounds almost poetic. They call it cosmic dawn, not because the universe suddenly burst into brightness all at once, but because the darkness began to soften. The first sources of light appeared. One by one, the earliest stars and galaxies began to illuminate the surrounding gas. The change was gradual. Imagine night giving way to morning, not with a sudden sunrise, but with scattered lanterns being lit across a vast landscape. At first you notice only one or two, then a few more appear. Eventually the darkness begins to lose its dominance. That slow illumination is what happened during cosmic dawn, and the galaxies Webb is detecting belong to this moment in the universe's story. Before those galaxies existed, the cosmos was filled with neutral hydrogen gas. That gas absorbed certain kinds of radiation very effectively. In particular, energetic ultraviolet light from stars could not travel far before interacting with the surrounding atoms. But when the first galaxies formed, they began pouring out enormous amounts of ultraviolet radiation. Young stars are powerful sources of that energy, especially the kind of massive stars believed to populate early galaxies. These stars burn hot and fast. Their surfaces blaze at temperatures far higher than that of our Sun, producing intense streams of ultraviolet photons. Those photons strike nearby hydrogen atoms and knock electrons loose. Once an electron is removed, the atom becomes ionized. As more stars ignite inside early galaxies, more radiation escapes into the surrounding gas. Ionized regions grow around each galaxy like expanding bubbles. At first, these bubbles are isolated. One galaxy creates a glowing region around itself. Another does the same somewhere else in the darkness. The universe becomes a patchwork of illuminated pockets surrounded by vast areas of neutral hydrogen. But the bubbles keep expanding. Over time, they begin to overlap. Two neighboring galaxies create bubbles that eventually merge, then three, then dozens. Gradually, across hundreds of millions of years, the neutral hydrogen fog that once filled the universe becomes increasingly ionized and transparent. This long transformation is what astronomers call the epoch of reionization. It marks the moment when the universe changed from an opaque cosmic fog into the transparent space we see today. The galaxies Webb is observing were part of the force that drove this transformation. They were not just passive structures drifting through space. They were engines of radiation and energy, shaping the state of the intergalactic medium around them. Each galaxy helped carve a growing region of ionized gas. And as more galaxies formed, those regions expanded until the universe as a whole became largely transparent to ultraviolet light. This transition had enormous consequences for cosmic evolution. Once space became transparent, radiation from distant galaxies could travel much farther without being absorbed. Light could cross immense stretches of space. That transparency is one reason we can detect galaxies across such vast distances today. But it also means that the galaxies Webb observes are located very close to the boundary between darkness and transparency. They lived in a universe that was still partly foggy. Some of their light travelled through regions of neutral hydrogen that absorbed specific wavelengths. Astronomers can actually see the effects of this absorption in the spectra of extremely distant galaxies. Certain wavelengths appear diminished or missing, revealing how intervening hydrogen clouds interacted with the light along its journey. This subtle imprint provides valuable clues about the state of the universe at that time. By analysing how much light is absorbed, researchers can estimate how much neutral hydrogen still filled space during different epochs. In other words, as distant galaxies act like backlights illuminating the cosmic fog. And Webb is observing those backlights with unprecedented clarity. But to fully appreciate how remarkable this is, we need to think about the journey those photons have taken. Consider a single photon emitted by a star in one of those early galaxies. It begins its life deep inside a stellar core where nuclear fusion converts hydrogen into helium, releasing energy. That energy works its way outward through the star's interior before finally escaping into space as light. Once the photon leaves the star, it enters interstellar space within its galaxy. Perhaps it travels through clouds of gas or dust, bouncing slightly off atoms along the way. Eventually it escapes the galaxy entirely and begins its journey across the universe. At that moment, the universe itself is only a few 100 million years old. Galaxies are rare. Most of space remains dark. The photon moves outward at the speed of light, about 300,000 kilometers per second. Every second it travels farther than light can circle Earth 7 times. In a single year, it covers nearly 10 trillion kilometers. But its journey is far longer than a year. It continues for millions of years, then tens of millions, eventually hundreds of millions. During that time, the universe expands. Space stretches continuously around the photon. Its wavelength slowly lengthens as the fabric of space itself grows. What began as ultraviolet light gradually shifts into visible wavelengths, then beyond red. Eventually it becomes infrared radiation. Still the photon continues. It passes through forming galaxies and evolving cosmic structures. Clusters of galaxies grow around it. Dark matter halos merge and reshape the large-scale web of matter across space. Entire civilizations rise and fall on distant planets long before the photon completes its journey. Billions of years pass. Finally, after travelling across more than 13 billion years of cosmic history, that photon arrives near a small blue planet orbiting an ordinary star in a spiral galaxy. It enters the golden mirror of the James Webb Space Telescope. The mirror reflects it onto a sensitive infrared detector. A tiny electrical signal is recorded. From that signal, astronomers reconstruct an image of a galaxy that existed when the universe was barely beginning to shine. This chain of events is almost impossible to grasp fully. One photon among trillions, travelling patiently across cosmic time, finally reaching an instrument built by a species that evolved billions of years after the photon began its journey. Yet that is exactly what Webb is doing. It is capturing ancient messengers from the first few 100 million years of existence. And those messengers are telling us that the early universe may have been far more lively than we once believed. Some galaxies appear to have formed stars at extraordinary rates. Their brightness suggests intense activity inside compact regions of space. Other observations hint that these galaxies may contain surprisingly mature stellar populations, stars that had already evolved through part of their life cycles. If that interpretation holds, it means that star formation must have begun even earlier than the galaxies we are currently observing. The cosmic dawn may have started sooner. Perhaps the very first stars ignited within 100 or 200 million years after the Big Bang. Those earlier stars may have lived fast and died quickly, enriching their surroundings and paving the way for the galaxies Webb now detects. If that is true, then Webb is not just observing the beginning of galaxies, it is observing a universe that had already experienced its first cycles of stellar life and death. Which leads us deeper into the mystery, because the first stars themselves remain almost entirely unseen. They were the pioneers that prepared the universe for everything that followed. Yet detecting them directly may be one of the greatest observational challenges in modern astronomy. Still, their fingerprints may already be hiding inside the galaxies Webb is revealing, and understanding those fingerprints could help us answer one of the oldest questions humanity has ever asked. How did the universe go from a simple cloud of hydrogen and helium to a cosmos filled with stars, planets, and eventually observers capable of looking back across 13 billion years of time? The answer may lie in the brief, brilliant lives of the very first stars that ever ignited. Long before the galaxies Webb now observes began to glow, the universe experienced a quieter moment of creation. This was the birth of the very first stars. Astronomers often call them population 3 stars, a slightly technical name that simply means they belong to the earliest generation. Unlike later stars, these pioneers formed in a universe that contained almost nothing except hydrogen and helium. No carbon, no oxygen, no iron. Those elements did not exist yet. Every heavier atom in the universe today, every atom in your bones, every atom in the oceans, every grain of iron inside Earth's core, had to be forged later inside stars. But the first stars had none of those ingredients available. They formed from pure primordial gas. This had profound consequences for how those stars behaved. In the modern universe, gas clouds collapse into stars relatively efficiently because heavy elements help the gas cool. When gas cools, it can compress more easily under gravity, allowing smaller fragments to form. Those fragments eventually become stars of many different sizes. That is why the Milky Way contains such a wide variety of stars, from small red dwarfs to massive blue giants. But in the early universe, the absence of heavy elements meant cooling was more difficult. The gas collapsing into the first stars likely remained hotter and more turbulent. Instead of fragmenting into many small stars, the collapsing clouds may have formed fewer but much larger ones. Computer simulations suggest that many of the first stars may have been tens or even hundreds of times more massive than our Sun. To picture that difference, imagine the Sun scaled up until its mass grew 100 times larger. Such a star would burn at extraordinary temperatures. Its surface would glow with intense ultraviolet radiation, and its lifetime would be astonishingly short by stellar standards. A star that massive might live only a few million years. Our Sun, by comparison, will shine for roughly 10 billion years. The first stars were cosmic fireworks. Brilliant, violent, and brief. During their short lives, they poured enormous amounts of radiation into the surrounding universe. Their ultraviolet light helped ionize nearby hydrogen, contributing to the gradual clearing of the cosmic fog. But their most important legacy came at the end of their lives. When massive stars exhaust their nuclear fuel, gravity overwhelms the pressure supporting them. Their cores collapse violently. In many cases, the outer layers explode outward in spectacular supernova explosions. Those explosions create new elements. Inside the extreme temperatures and pressures of stellar death, hydrogen and helium are fused into heavier atoms, carbon, oxygen, silicon, iron, and many others. When the star explodes, those elements scatter into surrounding space. This was the universe's first chemical enrichment. Before the first stars died, the cosmos was chemically simple. Afterward, new elements began spreading through interstellar gas, changing the way future stars and galaxies formed. Those heavy elements acted as cooling agents, allowing gas clouds to collapse more easily. They also became the building blocks for planets and eventually for complex chemistry. In a sense, the first stars transformed the universe from a simple environment into one capable of producing complexity. Yet observing those first stars directly remains incredibly difficult. They lived too early and too briefly. Most likely they existed before the galaxies Webb currently detects had fully assembled. Their light may have been faint and scattered across enormous distances. Instead of seeing the stars themselves, astronomers search for their fingerprints. One clue lies in the chemical composition of later stars. Some ancient stars in our galaxy contain extremely small amounts of heavy elements, suggesting they formed from gas that had only barely been enriched by earlier stellar explosions. Those stars act like fossils. Their chemical makeup preserves hints of the earlier stellar generations. Another clue may come from the galaxies Webb observes at extremely high redshift. If those galaxies formed after the first stars had already exploded, their gas may contain traces of heavy elements produced by those earlier supernovae. Spectroscopic observations can sometimes detect those elements, revealing whether the galaxy's gas has been enriched. In some early Webb observations, astronomers have indeed found evidence that heavy elements already existed in certain distant galaxies. This suggests that the universe had already gone through at least one cycle of stellar birth and death before those galaxies became visible. In other words, the first stars may have ignited even earlier than the galaxies we are currently observing. Cosmic dawn may have begun sooner than we once believed. But there is another fascinating possibility hiding within the story of those earlier stars, because some of them may have ended their lives in an even more dramatic way. When extremely massive stars collapse, their cores can sometimes form black holes. These black holes may have been the seeds of a phenomenon we observe throughout the universe today: supermassive black holes at the centers of galaxies. Nearly every large galaxy contains one. Our own Milky Way hosts a black hole weighing about 4 million times the mass of the Sun. Other galaxies contain black holes billions of times more massive. How such enormous objects formed remains one of astronomy's most intriguing puzzles. If the first stars were extremely massive, some may have collapsed directly into black holes weighing tens or hundreds of solar masses. Over time, those black holes could merge or rapidly accumulate surrounding gas, gradually growing into the supermassive objects we see today. Some early Webb observations have hinted at extremely active galaxies whose light may partly come from material falling into growing black holes. These objects appear surprisingly early in cosmic history. Again, the pattern repeats. The young universe may have been building structure faster than expected. Galaxies forming quickly. Stars igniting rapidly. Black holes emerging early. All of it happening within the first few 100 million years. But while these processes were unfolding, the universe itself was still expanding relentlessly. Every second, the distance between galaxies increased. Light traveling through space continued stretching. The cosmic web grew larger, and the galaxies Webb now observes slowly drifted farther and farther away from the region of space that would eventually become our local cosmic neighborhood. Today, those galaxies are unimaginably distant. Many of them are now tens of billions of light years away in terms of present-day separation. Their ancient light reached us only because it began its journey when the universe was far smaller. This means that when we observe those galaxies, we are not seeing where they are now. We are seeing where they were long ago. The universe has changed dramatically since then. Galaxies have merged, grown, and evolved. Clusters have formed. Entire new generations of stars have lived and died. Our own galaxy assembled gradually from smaller building blocks, incorporating stars born in ancient systems. Eventually the Sun formed from gas enriched by countless earlier stellar explosions. Around that young star, a small rocky planet coalesced from dust and debris. Billions of years later, life emerged, and eventually a species evolved capable of asking questions about the origins of everything around it. A species capable of building a telescope that can detect galaxies from the earliest epochs of cosmic history. That telescope is now quietly orbiting the Sun alongside Earth, watching faint infrared signals arrive from the distant past. Every observation it makes adds another piece to the story. Another glimpse of cosmic dawn. Another clue about how the universe learned to build galaxies, stars, and the complex structures we inhabit today. Yet even with Webb's extraordinary sensitivity, we are only beginning to explore this ancient era. There may be galaxies still farther away, still earlier, fainter lights that formed when the universe was even younger. And somewhere beyond the current limits of observation lies the true beginning of starlight itself. The moment when the first stars ignited in a universe that had never known light before. Webb is moving us closer to that moment, With each new deep observation, it pushes the boundary between the visible universe and the unknown a little farther back in time, and that boundary is approaching a moment so early in cosmic history that, eventually, we may witness the universe's very first lights beginning to flicker into existence. But before we push all the way to those first flickers of starlight, there is another quiet detail hidden inside Webb's observations that deserves attention. Because the galaxies we see at extreme distances are not only ancient, they are also incredibly small on the sky. When Webb images one of these early systems, the galaxy rarely appears as a grand spiral or an extended disk. Most of the time it is just a faint compact glow, sometimes only a few pixels wide in the detector. Yet within that tiny smudge of light may exist billions of stars. The reason we see them as such small points is simply distance. These galaxies are so far away that even entire galactic systems shrink to almost nothing against the background of space. To understand that scale, imagine holding a coin at arm's length. Now imagine trying to see a grain of sand resting on that coin from several kilometers away. That is roughly the challenge Webb faces when observing some of the earliest galaxies, and yet the telescope manages to do it. The secret is patience and sensitivity. When Webb stares at a distant patch of sky, it does not simply snap a quick photograph. It collects light slowly, minute by minute, hour by hour. The detectors accumulate faint photons arriving from galaxies billions of light years away. At first the signal looks almost like noise, tiny fluctuations in the detector's readings. But as more photons arrive, a pattern begins to emerge. A faint glow becomes visible, then a small shape. Eventually astronomers realize they are looking at a galaxy whose light left its stars when the universe itself was still in its early childhood. These deep observations are sometimes called deep fields. They are among the most powerful tools in observational astronomy because they allow telescopes to detect the faintest objects in the universe. Webb's deep fields reveal thousands of galaxies packed into tiny portions of sky. Some of them are relatively nearby in cosmic terms. Others are staggeringly distant. And among those distant objects, researchers have identified some of the earliest galaxies ever seen. What makes these observations even more remarkable is that the early universe itself was smaller. 13 billion years ago, the entire observable universe occupied a much smaller volume of space. Galaxies were physically closer together than they are today. So when Webb looks back to those early times, it is peering into a universe that was more compact and denser than the one we inhabit now. Imagine shrinking today's universe like a balloon slowly deflating. Galaxies that are now separated by tens of millions of light years would once have been much closer neighbours. This compression affects how galaxies grew. Interactions between young galaxies may have been more frequent. Collisions and mergers could happen more often, stirring gas and triggering bursts of star formation. These interactions may be part of the reason early galaxies sometimes appear brighter than expected. A galaxy collision can compress enormous clouds of gas, igniting thousands of stars almost simultaneously. The result is a temporary surge in brightness known as a starburst. If many early galaxies experienced such bursts, they could shine much more intensely than their mass alone would suggest. And when Webb observes them across cosmic time, it may be catching them during those brief luminous phases. But brightness alone does not tell the full story. Astronomers also look at the shapes and structures of these distant galaxies. Some appear compact and slightly irregular, with bright clumps of star formation scattered inside them. Others seem elongated or distorted, perhaps due to gravitational interactions with neighbouring galaxies. These shapes provide clues about how galaxies assemble themselves. In the modern universe, galaxies often settle into recognisable forms, spirals like the Milky Way or large elliptical systems dominated by older stars. But in the early universe, those structures were still forming. Gas flowed chaotically through young galaxies. Star formation erupted in bursts. Mergers reshaped entire systems. The result was a much more turbulent environment. Yet even within that turbulence, patterns began to emerge. Over billions of years, repeated mergers and gravitational interactions gradually built larger galaxies from smaller building blocks. The Milky Way itself likely formed this way. Long ago, it may have been composed of many smaller proto-galaxies that merged together over time. Even today, astronomers can trace remnants of those ancient mergers by studying the motions and chemical compositions of stars in our galaxy's halo. Some stars orbit the Milky Way in patterns suggesting they were born in entirely different galaxies that were later absorbed. So when Webb observes tiny galaxies in the early universe, we may actually be seeing the ancestors of much larger systems that exist today. Those faint distant objects could be the seeds from which galaxies like our own eventually grew. That idea brings a strange kind of intimacy to these observations. The ancient galaxies Webb detects are not merely distant curiosities. They may represent earlier stages of processes that ultimately produced the cosmic environment we inhabit. In other words, when we look at those faint infrared smudges from 13 billion years ago, we may be witnessing the first steps in the story that eventually led to the formation of the Milky Way, the Sun, and Earth itself. But the connection goes even deeper, because the same cosmic processes shaping those early galaxies continue operating today. Gravity still gathers matter into halos. Gas still collapses into stars. Stars still manufacture heavy elements in their cores. Supernova explosions still scatter those elements across space, enriching future generations of stars and planets. The universe remains dynamic. The difference is simply time. When Webb observes galaxies from less than 400 million years after the Big Bang, it is witnessing the beginning of a process that has been unfolding for nearly 14 billion years. And that beginning may hold clues about how quickly complexity can emerge in the cosmos. If galaxies were assembling rapidly so early, it suggests that the universe may have become structured sooner than once thought. Stars may have formed earlier. Heavy elements may have appeared sooner. Planets, and potentially habitable environments, might have become possible earlier in cosmic history. Of course, such possibilities remain speculative. Astronomers are cautious when drawing conclusions from early observations. New data will refine our understanding. Some candidate galaxies may shift slightly in estimated distance as measurements improve. Others may reveal new details when studied with deeper observations. Science advances step by step. Yet even at this stage, the message from Webb is unmistakable. The early universe was not a quiet, empty place waiting billions of years for structure to emerge. It was active, creative, full of rapid change. Within a few 100 million years after the beginning of cosmic time, gravity had already built dark matter halos. Gas had collapsed into those structures. Stars had ignited, lived, and died. Galaxies had begun shining across the expanding universe. And their light is reaching us now. Photons that left their stars before Earth existed are finally arriving at a telescope drifting through space near our planet. Each one carries information about a moment in cosmic history. And together, those photons are gradually revealing a universe that came alive astonishingly quickly after its birth. Yet there is still another layer to this story. Because the deeper Webb looks into the early universe, the more it challenges us to rethink something fundamental. Not the existence of galaxies, but the speed at which the cosmos learned to build them. For a long time, astronomers believed they had a fairly good picture of how quickly galaxies should appear after the Big Bang. The reasoning was straightforward. The universe began extremely hot and smooth. Tiny fluctuations in density slowly grew under gravity. Dark matter halos formed first. Gas fell into those halos. Stars ignited. Galaxies gradually assembled. But each step in that chain takes time. Gas must cool. Gravity must gather material. Stars must form in large enough numbers to make a galaxy visible across billions of light years. So most theoretical models predicted a kind of gradual ramp-up. The earliest galaxies would be small and faint. Only later, after hundreds of millions more years, would larger, brighter galaxies begin appearing in significant numbers. That expectation was not arbitrary. It was built from decades of simulations and observations that had worked well for much of cosmic history. Then Webb arrived and looked deeper than any telescope before it. And suddenly the earliest visible galaxies looked brighter than expected. Not impossibly bright, not so extreme that the entire framework of cosmology collapsed, but bright enough to make scientists pause and think carefully, because brightness in a galaxy usually means one of three things. It may contain many stars. Its stars may be unusually massive and luminous, or it may be undergoing a burst of star formation that temporarily floods the galaxy with light. When some of the first Webb deep field images were analysed, astronomers noticed several objects whose brightness suggested significant star formation was already underway when the universe was less than 400 million years old. In some cases, perhaps even earlier. Now pause for a moment and place that in perspective. The universe today is roughly 13.8 billion years old. 400 million years represents less than 3% of that entire history. If the age of the universe were compressed into a single day, these galaxies would appear in the first 40 minutes after midnight. And yet they are already shining, already forming stars, already part of an emerging cosmic web. For scientists who had spent years modelling galaxy formation, this raised a quiet but fascinating possibility. Maybe the early universe was simply very good at making galaxies. To understand why that might be true, consider how different the young universe was compared to the present day. The density of matter was higher. Everything was closer together. Gas streams feeding young galaxies may have been more abundant and easier to capture. Dark matter halos were forming quickly, merging, growing, pulling in material from their surroundings. In such an environment, once the first stars ignited, conditions could accelerate rapidly. Picture the difference between lighting a single match in an empty field and lighting a match in a dry forest. In the forest, once the first flame appears, the fire spreads quickly. The early universe may have behaved a little like that. Once the first stars began enriching their surroundings with heavier elements, cooling processes improved, gas could collapse faster, star formation could accelerate. Young galaxies might grow more quickly than earlier models predicted. Another subtle factor may involve the efficiency of star formation. In modern galaxies like the Milky Way, much of the gas does not immediately become stars. Magnetic fields, turbulence, radiation pressure, and stellar feedback all regulate the process. The conditions in the early universe may have allowed gas to convert into stars more efficiently in some environments. If that happened, galaxies could build bright stellar populations surprisingly quickly. Of course, astronomers do not jump to conclusions. The brightness of distant galaxies is difficult to interpret with complete certainty. Their light has travelled through enormous distances and cosmic environments. Dust, gas absorption, and stellar evolution models all influence the measurements. So researchers analyse these objects carefully. Spectroscopy provides one powerful method. Instead of simply measuring how bright a galaxy appears in several filters, astronomers spread its light into a detailed spectrum. This reveals precise wavelengths of emission and absorption lines produced by atoms inside the galaxy. Those lines act like barcodes. From them, scientists can determine redshift with far greater confidence. They can also estimate star formation rates, temperatures, and chemical abundances. With Webb's instruments, these measurements have become possible for galaxies deeper in cosmic time than ever before. And what they are revealing is consistent with a universe that became structured remarkably quickly. Not instantly, but sooner than many researchers once believed. The earliest galaxies appear to have assembled rapidly enough to begin lighting the universe within a few 100 million years. That may not sound dramatic at first, but remember the conditions of the early universe. At that time, there had been almost no heavy elements. The first stars had only recently exploded. Dark matter halos were still forming and merging. The cosmic web itself was still emerging, and yet galaxies were already appearing, already bright enough to be detected across 13 billion years of space. That realization has an interesting effect on how we think about cosmic history. It suggests that the transition from simplicity to complexity happened surprisingly quickly. From a hot uniform plasma to a universe containing stars and galaxies within a few 100 million years. From darkness to the first cosmic lights. From simple hydrogen gas to environments where heavier elements were beginning to appear, and eventually billions of years later to planets and observers capable of studying that entire sequence. But there is another subtle aspect of Webb's discoveries that often goes unnoticed. Because when astronomers detect extremely distant galaxies, they are not just measuring brightness and redshift. They are also observing something else. Time itself. When we look at nearby galaxies, we see them as they exist today. Their stars may be billions of years old. Their structures have evolved through countless mergers and transformations. But when we observe galaxies from the early universe, we are seeing them at an earlier stage of their lives. Sometimes a very early stage. It is a bit like opening a photo album of the cosmos. Nearby galaxies represent the present-day images. More distant ones show earlier chapters. and the galaxies Webb now observes belong to the earliest pages we can currently read. This ability to look backward through time is one of astronomy's most powerful tools. By studying galaxies at many different distances, astronomers can reconstruct how galaxies grow and evolve across cosmic history. They can watch structures emerge, change, merge, and mature. Webb is extending that photo album deeper into the past. And with every new page, the universe becomes more interesting. Some galaxies appear more mature than expected. Others seem compact and intensely active. Still others may represent systems in the earliest stages of formation. Each observation adds nuance to our understanding of cosmic dawn. And gradually a clearer picture emerges. The universe did not spend billions of years slowly building its first structures. Instead, once the first stars ignited, the process accelerated. Gravity pulled gas into halos. Stars formed. Supernovae enriched the gas. Galaxies grew brighter. Light spread across the cosmos. Within a few 100 million years, the universe had already begun producing the structures that would eventually evolve into the galaxies we see today. And that realization leads to one of the most humbling perspectives in all of astronomy. Because the light Webb is collecting tonight is not just revealing ancient galaxies. It is showing us the moment when the universe began to resemble something we can recognize. The moment when darkness started giving way to structure. When gravity, chemistry, and time began working together to build the cosmic landscape we now inhabit. And the deeper we look, the closer we move toward the very first sparks of that transformation. If we continue pushing that idea a little further, something quietly astonishing begins to emerge. The universe did not simply wait around for billions of years before becoming interesting. It became interesting very quickly. Within the first few 100 million years, gravity had already sculpted dark matter into halos large enough to gather gas. Inside those halos, the first stars had ignited. Some had already exploded, scattering new elements into space. Galaxies were forming, shining, interacting. All of that activity occurred before the universe had reached even 3% of its current age. In human terms, that would be like watching a child build an entire city before their second birthday. It suggests that the physical processes driving cosmic structure, gravity, gas dynamics, star formation, are extraordinarily efficient once the right conditions exist. And those conditions appeared almost immediately after the universe cooled enough for atoms to form. When Webb observes galaxies from less than 400 million years after the Big Bang, it is essentially watching the universe during its earliest phase of creative activity. The darkness has already begun to break. Stars are forming. Galaxies are emerging from the cosmic web. Yet the environment surrounding those galaxies still looks very different from the one we inhabit today. The intergalactic medium, the vast space between galaxies, still contains significant amounts of neutral hydrogen. Pockets of ionized gas surround the earlier star-forming systems, but the universe as a whole has not yet completed its transformation into the transparent cosmos we now observe. The fog is still lifting. In some directions, light travels freely across enormous distances. In others, it encounters clouds of hydrogen that absorb specific wavelengths. That patchwork transparency leaves subtle marks in the light reaching Webb's detectors. Astronomers sometimes detect a sharp drop in brightness at certain wavelengths when analyzing extremely distant galaxies. This feature, often called the Lyman break, occurs because neutral hydrogen absorbs ultraviolet light very strongly. When a galaxy lies at an enormous distance, the cosmic expansion stretches that absorption signature into infrared wavelengths. By identifying this pattern, astronomers can recognize galaxies that existed during the epoch of reionization. The technique is delicate, but it has become one of the key methods for identifying extremely distant objects in Webb's deep observations. And as those observations accumulate, they are gradually filling in a previously mysterious chapter of cosmic history. For decades, astronomers knew the cosmic microwave background showed us the universe when it was only about 380,000 years old. They also knew that by roughly 1 billion years after the Big Bang, galaxies had become common and well developed. But the interval in between, the first few 100 million years, remained difficult to observe directly. It was a kind of observational twilight zone. Too late to see with measurements of the cosmic microwave background. Too early for most telescopes to detect galaxies clearly. Webb is now illuminating that gap. The telescope's infrared sensitivity allows it to capture light that has been stretched across cosmic time from the first generations of galaxies, and that means we're finally beginning to observe the transition from darkness to light in the universe itself. What emerges from these observations is not a sudden event, but a gradual awakening. One galaxy ignites, then another. Star formation spreads across the cosmic web. Radiation from young stars pushes outward, ionizing hydrogen gas in expanding regions. Those regions grow and overlap until eventually the entire universe becomes mostly transparent. That transformation took hundreds of millions of years, but the galaxies Webb observes are among the earliest participants in that change. They are the pioneers of cosmic dawn, and because their light is travelling such extraordinary distances, we can use it to explore conditions that existed when the universe itself was still very young. That ability is powerful not only for understanding galaxies, but also for testing our broader theories of cosmology. For example, the rate at which galaxies appear over cosmic time provides clues about how dark matter behaves. If dark matter clumps too slowly, galaxies would take longer to form. If it clumps rapidly, galaxies could appear earlier. By measuring how many galaxies exist at different epochs, astronomers can compare observations with theoretical predictions. So far, Webb's discoveries appear broadly consistent with the idea that dark matter forms structures efficiently in the early universe. But the brightness and abundance of some galaxies suggest there may still be refinements to make in our models of star formation and galaxy growth. This is exactly how scientific progress unfolds. A new instrument reveals previously unseen phenomena. Existing theories are tested against the new data. Some predictions hold up remarkably well. Others require adjustment. Gradually the picture becomes clearer, and the universe becomes a little more understandable. Yet even as our understanding grows, the emotional impact of these observations remains difficult to ignore, because every one of those faint galaxies represents an extraordinary journey through time. The photons Webb detects left their stars long before the Earth formed, long before the sun began shining, long before the Milky Way assembled its spiral arms. Those photons travelled through an evolving universe for more than 13 billion years. Eventually, they encountered a small telescope orbiting near a small planet around a fairly ordinary star. And from that brief encounter, an image appears on a computer screen. A small smudge of light. But inside that smudge lies an entire galaxy from the dawn of cosmic history. It is easy to overlook how remarkable that is. Human beings evolved on a planet that formed billions of years after those galaxies existed. Yet within a tiny fraction of cosmic time, we developed mathematics, physics, and engineering sophisticated enough to build instruments capable of detecting them. A species that once wondered what the stars were made of can now observe galaxies that formed when the universe was still in its infancy. That realization places us in a curious position within cosmic history. We are late arrivals. Earth formed long after the first galaxies. Life emerged billions of years after cosmic dawn. But we're also early enough that the universe still preserves the light from those ancient events. The photons have not yet finished their journeys across space. They are still arriving, which means that right now, somewhere inside the instruments of the James Webb Space Telescope, new data is quietly accumulating. New photons are striking detectors. New galaxies are revealing themselves. Each observation pushes the boundary of our cosmic photo album a little further back in time. And somewhere ahead lies an even deeper goal. To see not just galaxies from 400 million years after the Big Bang, but perhaps galaxies from 200 million years, or even earlier. And if those observations succeed, we may eventually glimpse the faint signatures of the very first stars themselves, the moment when the universe's long darkness finally gave way to the first sparks of starlight. There is a quiet limit hidden inside every telescope. No matter how powerful an instrument becomes, it cannot see indefinitely into the past. At some point, the universe itself becomes opaque, and light from earlier times simply cannot reach us. For much of modern astronomy, that boundary has been the cosmic microwave background. That faint radiation fills the universe in every direction. It represents the moment when the universe cooled enough for atoms to form, roughly 380,000 years after the Big Bang. Before that moment, the cosmos was a dense plasma where light scattered constantly off charged particles. Photons could not travel freely, so the microwave background forms a kind of cosmic wall. Beyond it, ordinary light cannot reveal anything. But between that wall and the galaxies Webb now observes lies a vast stretch of time. Hundreds of millions of years. That interval contains the birth of the first stars, the formation of the first galaxies, and the gradual illumination of the cosmic web. Until recently, most of that era existed mainly in theory. Astronomers ran enormous computer simulations to model what might have happened during those early epochs: gravity, dark matter, gas dynamics, star formation. All of these ingredients were placed inside the virtual universe of supercomputers. Those simulations predicted the growth of dark matter halos, the collapse of gas, the ignition of the first stars. They predicted how the cosmic web should evolve. They predicted when galaxies should begin appearing in large numbers. But simulations are not the same as observation. They are powerful tools, yet they always depend on assumptions about the physics involved. Observational data is what ultimately tests those assumptions. And this is precisely what Webb is now providing. Instead of relying only on models, astronomers can examine actual galaxies from those early periods. Each galaxy becomes a data point in the timeline of cosmic evolution. By counting how many galaxies appear at different distances, researchers can reconstruct how quickly star formation spread through the young universe. By measuring their brightness and spectra, they can estimate how massive those galaxies are and how rapidly they are forming new stars. By studying the distribution of galaxies across the sky, they can map how structure was emerging within the cosmic web. Gradually, the observational gap between the cosmic microwave background and the well-developed galaxies of later epochs is being filled. But even as Webb pushes deeper into the past, another intriguing idea comes into view. Because the earliest galaxies we observe may not represent the true beginning of cosmic structure. They may simply be the earliest objects bright enough for us to detect. There may have been smaller galaxies before them, dimmer ones, systems containing only a few million stars instead of billions. Such galaxies might have existed earlier than the ones Webb currently detects, but their light may be too faint to see across 13 billion years of space. In other words, we may still be missing the very first generation of galaxies. Finding them is one of the next great challenges in observational cosmology. Astronomers are already planning ways to push Webb's capabilities further. Longer exposure times can reveal fainter objects. Observing multiple deep fields across different regions of sky increases the chances of finding extremely rare early systems. Gravitational lensing provides another powerful technique. Massive galaxy clusters can bend and magnify the light from galaxies lying far behind them. This effect, predicted by Einstein's theory of general relativity, acts like a natural cosmic telescope. When Webb observes regions behind massive clusters, distant galaxies may appear brighter and larger than they otherwise would. This magnification sometimes reveals galaxies that would be too faint to detect directly. Using these gravitational lenses, astronomers hope to push the observational frontier even closer to cosmic dawn. And with each step deeper into the past, the same quiet question returns. How early did the universe begin forming stars? Did the first stars ignite 100 million years after the Big Bang? 200 million? Even earlier? Webb's observations are beginning to narrow that window. But another, more subtle question lies beneath the surface. Why does the universe produce stars and galaxies at all? Gravity alone explains part of the story. Matter attracts matter. Dense regions grow denser. Gas collapses under its own weight. But the emergence of stars and galaxies requires a delicate balance between many physical processes. Cooling mechanisms must allow gas to collapse efficiently. Radiation from early stars must escape their galaxies to ionize surrounding gas. Supernova explosions must enrich the environment with heavy elements without completely disrupting future star formation. All of these processes interact across enormous scales of space and time. Yet somehow the result is a universe filled with luminous galaxies. A universe capable of producing planets. Eventually, a universe capable of producing observers. When Webb observes galaxies from less than 400 million years after the Big Bang, it is revealing how early that process began. It shows us that the path from primordial simplicity to cosmic structure was already underway almost immediately after the universe cooled enough to allow atoms to form. From a broader perspective, this is deeply reassuring for cosmology. The basic framework describing the universe, the Big Bang, cosmic expansion, dark matter, gravitational structure formation, continues to explain the overall picture remarkably well. What Webb is refining are the details: the speed of galaxy growth, the efficiency of early star formation, the timing of cosmic reionization. These refinements make the story richer, more precise, more vivid, and they remind us that the universe is not static knowledge carved permanently into textbooks. It is an unfolding investigation. Each generation of instruments pushes the boundary of what we can observe. Hubble revealed galaxies billions of years in the past. Webb is revealing galaxies near the dawn of cosmic time. Future observatories may push even deeper, detecting fainter systems or mapping the earliest phases of star formation through new techniques. Perhaps one day astronomers will even detect the direct signatures of the first individual stars. For now, the galaxies Webb has already revealed are more than enough to reshape our sense of cosmic history. They show that by the time the universe was only a few 100 million years old, the first great chapter of structure formation was already well underway. Galaxies were forming, stars were shining. Heavy elements were beginning to circulate through space. The cosmic web was taking shape, and from those beginnings would grow everything that followed. Clusters of galaxies, supermassive black holes, planetary systems, and eventually, somewhere inside one unremarkable galaxy, a species capable of building a telescope powerful enough to look back across almost the entire history of existence. A species capable of seeing the universe when it was still young, still forming its first galaxies, still learning how to shine. If we continue following that thread, something subtle becomes clear about what Webb is really giving us. It is not simply showing us distant galaxies. It is giving us access to a stretch of time that, until recently, was almost entirely hidden. For decades, astronomers had two clear snapshots of the universe's past. One came from the cosmic microwave background, showing the cosmos when it was about 380,000 years old. The other came from observations of galaxies when the universe was already more than 1 billion years old. Between those two moments lay hundreds of millions of years of missing detail. It was as if we had photographs of a person as a newborn, and then another as a fully grown adult, but almost nothing from childhood. Webb is beginning to fill in that childhood, and the early pictures it is revealing are already rich with activity. Galaxies forming, stars igniting, gas swirling through dark matter halos, radiation slowly transforming the intergalactic medium. But as we explore this era more deeply, something else becomes apparent. The universe was not simply building isolated galaxies. It was building networks. Even the earliest galaxies were not alone in empty space. They formed along the invisible filaments of the cosmic web, where dark matter and gas were most concentrated. Along those filaments, galaxies could interact with one another. Gas could flow from one region to another. Gravitational forces could pull small systems together into larger ones. These interactions likely played an important role in how quickly galaxies grew. When two small galaxies drift close together, gravity begins to reshape them. Gas clouds collide and compress. Star formation may erupt across the merging system. For a short period of time, the galaxy becomes much brighter. These events are called starbursts. They are brief compared to cosmic timescales, perhaps lasting tens of millions of years, but during that period the galaxy can shine intensely. If many early galaxies experienced frequent mergers, then bursts of star formation could have been common in the young universe. This would help explain why some of the galaxies Webb observes appear unusually luminous. It also suggests that the early universe was not a calm place. It was crowded, dynamic. Young galaxies were forming, merging, reshaping themselves again and again. From those repeated interactions, larger and more stable galaxies eventually emerged. We can actually see echoes of that history even in our own galaxy today. The Milky Way contains stars that did not originally form here. Their motions through the galaxy reveal that they came from smaller systems that were absorbed long ago. Astronomers have identified streams of stars stretching across the sky, remnants of dwarf galaxies that were torn apart by the Milky Way's gravity. Those stellar streams are fossils of ancient mergers. They remind us that galaxies grow through accumulation, through gravity slowly gathering smaller pieces into larger structures. When Webb observes tiny galaxies in the early universe, we may be seeing the earliest building blocks of that process. Some of those distant galaxies may eventually merge into larger systems. Others may remain relatively small, becoming dwarf galaxies orbiting larger hosts. Over billions of years, the cosmic web channels matter into larger and larger structures. Clusters of galaxies form at the intersections of the web's filaments. Inside those clusters, galaxies orbit one another under the influence of immense gravitational fields. Some collide, some merge, some are stripped of gas and stars. The universe never stops evolving, but the galaxies Webb observes represent the beginning of that long story. They are the earliest visible nodes in a cosmic network that would eventually stretch across billions of light years. Another fascinating detail lies in the colours of these distant galaxies. Because their light has been stretched so dramatically by cosmic expansion, most of the radiation we detect from them lies in the infrared. Webb's detectors capture this faint glow and convert it into images we can interpret. Sometimes the galaxies appear reddish in Webb's processed images, not because they are actually red in their own frame of reference, but because their ultraviolet and visible light has been stretched across cosmic time. This stretching, known as redshift, is the key to measuring distance in the universe. The greater the redshift, the longer the light has been travelling, and therefore, the earlier the time we're observing. Some galaxies detected by Webb have redshifts suggesting that their light began its journey when the universe was less than 400 million years old. Each one represents an observation near the edge of the visible cosmic past. And yet, even at that distance, the galaxies still appear structured, still forming stars, still participating in the grand process of cosmic evolution. It is difficult not to feel a quiet sense of awe when considering what this means. For billions of years after those galaxies formed, the universe continued evolving without us. Stars were born and died. Galaxies merged and reshaped themselves. Heavy elements spread through space. Planetary systems emerged. Eventually, one of those systems produced a small world covered in oceans and atmosphere. Life arose, and after an immense stretch of time, that life developed curiosity, a desire to understand the sky. Humans began building telescopes. At first, they were simple instruments, glass lenses pointed at the moon and planets. Then larger mirrors appeared. Observatories grew more sophisticated. Space telescopes began orbiting above Earth's atmosphere. With each generation, our ability to see deeper into space improved. And with each improvement, our window into the past expanded. Now Webb has extended that window almost to the beginning of the age of galaxies. It allows us to observe the universe during its earliest period of cosmic creativity. Not through theory alone, not through simulations, but through direct observation. We are literally seeing galaxies that existed when the universe itself was still very young. And the more Webb observes, the more the early universe begins to feel like a real place rather than an abstract era of equations. A place where stars ignited inside collapsing clouds of hydrogen, where galaxies emerged along invisible rivers of dark matter, where light began spreading across a universe that had previously been almost completely dark. The fact that we can see those moments at all is extraordinary. But it also raises one final perspective worth holding on to, because the photons arriving from those ancient galaxies are not the last messages they will ever send. They are simply the first ones reaching us now. Even as you listen to this story, new photons are leaving those galaxies. Light from stars that formed billions of years after the ones Webb currently observes is still travelling across space. Those photons will continue moving through the expanding universe for billions more years before they reach whatever observers may exist in the distant future. Cosmic history is not finished. The universe is still writing new chapters. But thanks to the James Webb Space Telescope, we are now able to read the earliest pages of that story with a clarity no human generation has ever possessed. And those pages reveal something beautiful. The universe did not take long to begin shining. Something else quietly remarkable appears when you step back and think about what Webb is actually doing. It is not just showing us distant galaxies. It is letting us measure how quickly the universe changed from a simple place into a complex one. Because the early universe began in an almost unbelievably smooth state. Right after the Big Bang and the formation of the cosmic microwave background, matter was spread through space, with only the faintest variations in density. Imagine a perfectly calm ocean with barely noticeable ripples. Those tiny ripples were the seeds of everything. Gravity slowly amplified them. Slightly denser regions pulled in surrounding material. Over time they became the first dark matter halos. Gas collected inside them. Stars ignited. Galaxies formed. But the speed of that transformation has always been an open question. How long does it take for a universe to go from nearly uniform gas to luminous galaxies? 1 billion years? 500 million? Less? Webb is giving us the first direct measurements of that transition, and the answer appears to be surprisingly fast. Within just a few 100 million years after the Big Bang, the universe had already produced galaxies bright enough to be seen across 13 billion years of space. To feel that timescale properly, imagine compressing the entire age of the universe into a single year again. The cosmic microwave background would appear around the first minute of January 1st. The galaxies Webb now observes would form sometime in the early days of January. Meanwhile, Earth would not appear until early September. Human civilization would occupy the final seconds before midnight on December 31st. In that compressed timeline, the universe spent only a few days learning how to build galaxies. Everything that followed, the Milky Way, the Sun, the Earth, life, telescopes, came much later. This perspective changes the emotional texture of cosmic history. The early universe was not a long empty prelude waiting billions of years before anything interesting happened. Instead, it was a period of astonishing creativity. Gravity moved quickly. Gas collapsed. Stars ignited. And galaxies began shining across the expanding universe almost immediately after conditions allowed it. Another intriguing clue comes from the shapes and sizes of the earliest galaxies Webb detects. Many appear extremely compact. Their light is concentrated into very small regions, suggesting intense star formation occurring inside dense pockets of gas. In some cases, the stars in these galaxies may be packed far more tightly than those in the calm spiral arms of galaxies like the Milky Way. Picture a city skyline at night. Some cities spread their lights across wide suburbs and highways. Others compress enormous numbers of lights into a small downtown core filled with skyscrapers. Early galaxies may have resembled those dense cores, small regions producing huge amounts of light. Such conditions could produce stars at extraordinary rates. Gas flowing along the cosmic web may have poured into these galaxies continuously, feeding new waves of star formation. At the same time, supernova explosions from massive stars would inject energy into the surrounding gas, stirring turbulence and sometimes triggering the collapse of new star-forming clouds. It was a chaotic but fertile environment, and through that chaos, galaxies gradually assembled themselves. Over time, repeated mergers and gravitational interactions would smooth some of that turbulence. Larger galaxies would grow from the accumulation of smaller systems. Disks would form, spiral arms would emerge. But in the earliest epochs, galaxies were still young and irregular. Webb's images capture them in that early stage. Not yet settled, still assembling, still gathering the stars that would eventually shape their long futures. And yet even in that youthful form, they shine brightly enough for us to see them across nearly the entire history of the universe. Which brings us to another quiet realization. Every galaxy Webb detects at extreme distance represents a survivor. The universe is vast, and not every early galaxy will endure unchanged for billions of years. Some will merge into larger systems. Others may be stripped apart by gravitational interactions. Still others may exhaust their gas and fade into faint remnants. But the galaxies whose light we detect today manage to produce enough stars, enough radiation, to send photons on journeys lasting more than 13 billion years. Those photons are still arriving, and when they do, they bring with them a picture of the universe during its earliest era of structure. That picture continues to grow sharper as Webb collects more data. Each new observation refines our estimates of how many galaxies existed at different epochs. Each spectrum reveals new details about their stars and gas. Each deep field uncovers fainter objects that were previously invisible. Gradually, astronomers are mapping the rise of galaxies across cosmic time, and the map is beginning to look surprisingly busy even at very early stages. It is possible that future observations will reveal galaxies from even earlier times, perhaps 200 million years after the Big Bang. If that happens, we will be seeing the universe when it was barely 1% of its current age. At that point, we would be observing cosmic history almost at the moment when the first sustained star formation began. Reaching that era will require extraordinary patience and sensitivity. The galaxies from that time are likely faint and rare, but the progress already made suggests it may be possible. And if Webb, or future telescopes, manage to detect them, The result would bring us even closer to witnessing the birth of the first galaxies themselves. Yet even without going further back, the galaxies Webb has already revealed tell us something profound. The universe does not need billions of years to begin building complexity. Once the fundamental ingredients exist, gravity, gas, and time, the process begins almost immediately. Stars ignite, galaxies form, light spreads across space, and those first lights are still travelling through the universe today. Some of them are reaching us now, captured by a telescope drifting quietly in the darkness nearly 1.5 million kilometres from Earth. A telescope built by a species that did not exist when those photons began their journey. A species that has learned, in a relatively short moment of cosmic history, how to look backward across 13 billion years and watch the universe awakening. And the deeper we look, the clearer it becomes that cosmic dawn arrived sooner than anyone once imagined. For most of human history, the night sky gave the impression of permanence. The stars appeared fixed in place. The same constellations rose and set across generations. Ancient civilizations separated by thousands of years looked upward and saw almost exactly the same patterns. It was natural to assume the universe had always been that way. But modern astronomy slowly revealed something very different. Stars are born. They age. They die. Galaxies collide and merge. Even the universe itself evolves. The James Webb Space Telescope extends that realization all the way back to the earliest visible chapters of cosmic history. It shows us that the universe was not always filled with galaxies. There was a time before them, a time when space contained only simple gas, hydrogen and helium drifting through expanding darkness. Then, slowly at first, gravity began gathering that gas into invisible wells shaped by dark matter. Inside those wells, the first stars ignited. From those stars, the first galaxies emerged. And Webb is showing us that this transformation happened astonishingly early. When the universe was less than 400 million years old, galaxies were already forming and shining across the cosmic web. That number can still feel abstract, so it helps to compare it with something familiar. The Earth is about 4.5 billion years old. Life on Earth has existed for nearly 4 billion years. But the galaxies Webb is observing existed long before any of that. Their light began travelling across space more than 9 billion years before the Earth itself formed. If the universe were a long novel, those galaxies belong to the opening chapters, written before the setting and characters we know had even appeared. Yet somehow the pages survived. The photons carrying that ancient light crossed nearly the entire length of cosmic history without being destroyed. Eventually they encountered a mirror floating in deep space. A mirror carefully shaped, polished, and launched by a species that evolved billions of years after those galaxies first shone. That mirror reflected their light into detectors. And suddenly, on a screen inside a research laboratory on Earth, a faint smudge appeared. A tiny mark of light. But inside that smudge lies an entire galaxy from the dawn of time. And when astronomers analyze that light, they begin to reconstruct the story of how the universe learned to build structure. How dark matter halos gathered gas. How the first stars ignited. How early galaxies assembled themselves from swirling clouds of hydrogen. How radiation from those galaxies began transforming the surrounding universe. Piece by piece, the story becomes clearer. The cosmic dark ages ended earlier than we once thought. Star formation accelerated quickly. Galaxies appeared sooner. Light spread across the universe while it was still very young. This realization carries a quiet emotional weight, because it reminds us that complexity can arise from simplicity with surprising speed. From a nearly uniform cloud of hydrogen gas, gravity and time produced galaxies. Inside those galaxies, stars forged the heavier elements needed for planets. Around some of those stars, worlds formed. And on at least one of those worlds, chemistry eventually became biology. Biology became intelligence. And intelligence built instruments capable of looking back across almost the entire history of existence. That chain of events is breathtaking when you think about it. It links the first stars to the present moment. The galaxies Webb observes are not just distant objects. They are part of the same cosmic story that eventually produced everything around us. The oxygen in the air you breathe, the carbon in your cells, the calcium in your bones, all of it originated inside stars. And those stars formed inside galaxies. galaxies whose earliest ancestors are now being observed by Webb near the dawn of cosmic time. When we look at those faint distant systems, we're seeing the early stages of the processes that ultimately produced the Milky Way. Our galaxy likely grew from smaller structures similar to the ones Webb now detects. Over billions of years, mergers and gravitational interactions built larger and more stable galaxies. Stars formed generation after generation. Heavy elements accumulated. Eventually, the environment became rich enough for planetary systems like our own to emerge, which means the distant galaxies Webb observes are not entirely separate from us. They are connected to the deep ancestry of cosmic structure. They represent earlier steps in the long chain of events that led, eventually, to observers capable of studying them. And yet those galaxies themselves have continued evolving. The ones whose ancient light Webb detects have changed dramatically during the 13 billion years since those photons began their journey. Their stars have aged. Their structures have grown. Some may have merged with neighbouring galaxies. Others may now exist as massive systems surrounded by countless generations of new stars. We are seeing them only as they once were, a brief moment in their long history. That is one of the quiet wonders of astronomy. Looking deeper into space means looking further into the past. Every telescope image becomes a time capsule, and Webb is opening some of the oldest time capsules humanity has ever found. Inside them are the earliest galaxies we can currently observe. Small luminous islands in a universe that was only beginning to shine. Yet even as extraordinary as that is, the story may not end there, because the boundary of what Webb can detect is not the final boundary of cosmic history. Beyond the galaxies we see now may lie even earlier ones. Fainter systems, dimmer sparks of star formation occurring closer to the moment when the very first stars ignited. Astronomers are still searching, still observing, still pushing the frontier deeper into the past. Each new discovery brings us closer to answering one of the oldest questions humans have asked when looking at the night sky. When did the universe first begin to shine? The James Webb Space Telescope has brought us closer to that answer than ever before. And in doing so, it has revealed a universe that came alive astonishingly quickly after its birth. When you sit quietly with that idea, the night sky begins to feel different. For thousands of years, people looked up and saw stars scattered across darkness. Some imagined them as distant fires. Others believed they were fixed lights embedded in a celestial sphere. For most of human history, there was no way to know how deep that darkness truly went, or how far back the story of those lights might reach. Now we know the sky is not a ceiling. It is a timeline. Every point of light carries a delay. The farther away the source, the longer the delay becomes. Nearby stars show us years or centuries into the past. Distant galaxies reveal millions or billions of years. And with instruments like the James Webb Space Telescope, that delay stretches almost to the beginning of cosmic history itself. When Webb observes galaxies from less than 400 million years after the Big Bang, it is showing us the universe while it was still forming its earliest patterns of structure. The cosmic web was young. Dark matter halos were still gathering gas. Stars were igniting for the first time in many regions of space. Those galaxies were among the earliest sustained sources of starlight in existence. Their radiation helped transform the surrounding universe, gradually lifting the fog of neutral hydrogen that filled space after the cosmic dark ages. And yet, when we observe them today, their light arrives quietly. It appears as faint infrared signals striking detectors inside a telescope drifting far from Earth. A whisper from the deep past. But within that whisper lies a tremendous amount of information. Astronomers analyze the brightness of these galaxies to estimate how many stars they contain. They study the distribution of their light to understand how those stars are arranged. Spectra reveal the presence of chemical elements produced by earlier stellar generations. Each observation adds another clue. Gradually, the earliest period of galaxy formation becomes less mysterious. We begin to see how gravity, gas, and time work together to build the first luminous structures in the universe. What Webb is revealing is not a sudden explosion of complexity. It is a steady unfolding. At first, small stars ignite inside dense clouds of primordial gas. Those stars enrich their surroundings with heavier elements when they die. Gas cools more efficiently. New generations of stars form. Galaxies grow brighter. Radiation spreads outward, ionizing hydrogen across the cosmic web. Over hundreds of millions of years, the universe transitions from darkness into light. That transformation is one of the great turning points in cosmic history. Before it, the universe was largely invisible. After it, galaxies filled space with starlight. The structures we see today, spiral galaxies, elliptical galaxies, galaxy clusters, are all descendants of that early era. But the galaxies Webb observes are not yet those mature systems. They are young, compact, often irregular in shape. They are galaxies still in the act of becoming. Their stars burn fiercely. Gas flows through them along the filaments of the cosmic web. Supernova explosions stir their interiors, shaping future generations of star formation. They are laboratories of cosmic evolution, and yet their light has survived across 13 billion years of expanding space. During that time, the universe itself has changed enormously. Galaxies have grown larger. Clusters of galaxies have formed. Supermassive black holes have become common at galactic centers. New stars have been born from gas enriched by countless earlier stellar deaths. Our own galaxy assembled through a long sequence of mergers and growth. Eventually the Sun formed within a cloud of enriched gas. Around it, planets condensed. On one of those planets, chemistry eventually crossed the threshold into biology. And billions of years later, life developed the ability to ask questions about its origins. All of that unfolded while the photons Webb detects tonight were still travelling through space. That realization creates a strange sense of overlap between past and present. The galaxies Webb observes existed when the universe was only a few 100 million years old, but the light reaching us from them has been travelling ever since. Those photons are arriving now. Right now, detectors aboard a telescope floating in deep space are registering signals from galaxies that shone long before Earth existed. This is what makes astronomy different from almost every other science. In most fields, we study objects in their present state. Astronomy allows us to watch history unfolding across enormous spans of time. The deeper we look into space, the further back we see. And Webb has extended that view almost to the beginning of the age of galaxies. There is still further to go. Beyond the galaxies Webb detects today lie even earlier times. Somewhere beyond our current observational limits, the very first stars ignited inside collapsing clouds of primordial gas. Those stars lived fast and died young. They forged the first heavy elements. They changed the chemistry of the universe forever. Finding their direct signatures remains one of the great goals of modern astronomy. Perhaps Webb will glimpse them through indirect clues in extremely distant galaxies. Perhaps future telescopes will detect them more clearly. But regardless of how that search unfolds, the discoveries already made have transformed our sense of cosmic history. We now know that the universe began building galaxies far earlier than we once imagined. Less than 400 million years after the Big Bang, entire systems of stars were already shining across space. The darkness had begun to lift. And that realization leads naturally to one final perspective. Because the photons Webb detects tonight are not the last light those galaxies will ever send. Even now, new stars are forming inside them. New photons are leaving their surfaces. Those photons will travel across the expanding universe just as the earlier ones did. They will cross billions of years of cosmic evolution, and far in the future, they may reach observers living around stars that have not yet formed. Those distant observers may build their own telescopes. They may look back across time and see galaxies as they existed billions of years before their own civilizations emerged. In that sense, the universe is constantly sending messages forward through time. Every star, every galaxy, every burst of light becomes part of an enormous archive carried by travelling photons. The James Webb Space Telescope has simply opened one of the oldest archives we have ever been able to read. Inside it are galaxies from the dawn of cosmic history, small lights shining in a universe that had only just begun to glow. And when we look at them, we are witnessing something both ancient and deeply personal. We are seeing the universe at the moment it first began to resemble the one we know today. And when you let that idea settle for a moment, the ordinary sky begins to feel a little less ordinary. Because what Webb has really shown us is not just a set of distant galaxies. It has shown us how quickly the universe began building the structures that would eventually lead to everything we see around us. Less than 400 million years after the beginning of time, galaxies were already shining. That fact alone changes how we imagine the early cosmos. For a long time, it was tempting to picture the young universe as quiet and empty for vast stretches of time. A slow beginning followed by gradual growth, but the evidence now suggests something more energetic. Once the universe cooled enough for atoms to form, gravity began shaping matter almost immediately. Dark matter gathered into halos. Gas streamed along the invisible filaments of the cosmic web. The first stars ignited. Galaxies assembled from those early sparks of light. The transformation from simplicity to structure happened quickly. And those first structures are still visible today, not as they exist now, but as they were long ago. The galaxy's Webb observes are ancient snapshots. They are moments frozen in light. Each photon arriving at the telescope represents a tiny piece of history, travelling across billions of years to reach a mirror floating far beyond Earth's atmosphere. When those photons are collected together, they reveal an entire landscape from the early universe. Small galaxies glowing against a still dark cosmic background. New stars blazing inside dense clouds of primordial gas. Radiation spreading outward into the intergalactic medium, slowly dissolving the fog that once filled space. It was the beginning of the luminous universe. Yet there is something deeply calming about realizing how continuous the story has been. The processes shaping those early galaxies are the same ones still operating today. Gravity still gathers matter. Gas still collapses into stars. Stars still forge heavy elements in their cores. Supernova explosions still scatter those elements into space, preparing the material for future generations of stars and planets. The universe has not changed its rules. It has simply had more time. More time for galaxies to merge and grow. More time for stars to form and die. More time for chemistry to become richer and more complex. Eventually, enough time for planets to appear around stars enriched by countless earlier stellar explosions. And on at least one of those planets, enough time for life to arise. That life eventually developed curiosity. The same curiosity that led humans to look up at the night sky and wonder what the stars really are. For thousands of years, those questions remained unanswered. Then, slowly, the answers began to appear. Telescopes revealed that stars are distant suns. Spectroscopy revealed their chemical composition. Radio telescopes discovered the faint afterglow of the Big Bang. Space telescopes began imaging galaxies billions of light-years away. And now, with the James Webb Space Telescope, we're observing galaxies from the dawn of cosmic history itself. The first few 100 million years of the universe are no longer hidden behind theory alone. They are visible, faint, distant, but real. And perhaps the most remarkable part of this story is that the photons carrying that ancient light are still arriving. They are not relics stored somewhere in space. They are travelers moving continuously across the universe. Some left their galaxies billions of years ago, and only now are reaching our detectors. Others are still on their way. Even as you listen to these words, new photons are entering Webb's mirrors. Each one adds another small piece to the picture of cosmic dawn. Astronomers will spend years studying those signals. New galaxies will be catalogued. Redshifts will be measured more precisely. The timeline of early galaxy formation will become sharper. Some mysteries will be resolved. New ones will appear. That is the nature of science. But one truth is already clear. The universe did not wait long before it began to shine. Within a few 100 million years of its birth, gravity had gathered matter into galaxies. Stars were blazing across the young cosmic web. Radiation was transforming the surrounding darkness into a transparent universe filled with light. And 13 billion years later, that ancient light is still travelling. It crosses the expanding fabric of space until, by extraordinary coincidence, it encounters a small telescope built by curious beings on a quiet planet. The telescope records the signal. A faint galaxy appears on a screen. A moment from the dawn of time becomes visible again. And somewhere inside that faint glow lies a reminder that the universe has been telling its story from the very beginning. We simply had to learn how to listen. Tonight, with the James Webb Space Telescope, we finally can,